All right. So, okay, our next speaker is Jon Hobbs from JPL. So, go ahead.
All right, thank you. It's great to be here. I appreciate the invitation. So I'm going to talk about, I think in the introductory slides that Anne showed, one of the theme areas that Stamps is thinking about a lot is remote sensing. So I'm going to talk about that and the work that we're doing at the Jet Propulsion Laboratory. This is going to be focused on remote sensing of the Earth and applications for the carbon cycle. And this is work with our team on uncertainty quantification at JPL and some external collaborators. So just a quick overview of the outline here. I'm going to introduce NASA's Earth Science remote sensing fleet and then talk a little bit. I think when I was thinking about the theme of the workshop and trustworthy statistical inference, one of the things that drives a lot of the objectives for Earth Science remote sensing is what's called traceability. So I'm going to introduce that as well and sort of revisit that throughout the rest of the talk. And then I'll sort of step through the data product pipeline and the inference pipeline for these products as they are done in the carbon cycle, observing the carbon cycle. So to start things off here, this slide talks about the NASA's Earth Science observing fleet, and the figure here is a depiction of all of NASA's assets currently and planned for the future for observing the Earth. And so kind of the way to read this is in this spiral that goes around the figure here at the very inside of the spiral are some of the oldest instruments that are still in operations. And so the first few here are Terra Aqua and Aura, which are a generation of satellites that were deployed over 2 decades ago and are still monitoring the Earth system from space. And then as you sort of work your way out of the spiral, here are more recently deployed instruments. And then there's sort of a special collection here in the middle that represent instruments that are all on the International Space Station. So as we sort of work our way out, there's one here called OCO2, which is the Orbiting Carbon Observatory 2, and I'll spend some time talking about that in this presentation. And in addition to that, there's OCO3, which is actually on the ISS and is a companion instrument for OCO2. So as we work our way out here to the current time, there's actually this figure is slightly out of date. Some of the most recent instruments that have been launched was NISAR last year. And then there's a few that are in planning. Some of them have been renamed and rescoped a little bit, but that's sort of the lay of the land. And so all of these assets are managed as what NASA calls missions. And as I'll talk about with this notion of traceability, the design for these missions is informed by science objectives. And if they're successful, a lot of times they can last well beyond the nominal plans for the mission. A lot of these missions are initially planned and scoped for a few years to 5 years. But as you can see here, they can oftentimes last a lot longer than that. And the science story for those missions evolves as time goes on. So I want to talk next about this idea of traceability. And when these missions are designed and actually proposed, a big piece of the story is what sort of science they're going to inform. And they actually put together what's called a science traceability matrix. And there's an example here on the bottom that was for the fairly recently launched Psyche mission. That's actually a planetary mission, not an Earth mission, but all of these missions have to put together this science traceability matrix. And it basically starts with, on the left in this figure, very broad science goals and works its way across to actual science and measurement objectives that relate to those goals, and then continues to work across to how instruments are going to be designed and what they're actually going to measure and what the requirements are for the instrument or instruments. And then a big one that I'm going to talk about as we go along here is all of these missions are directed to produce data products for use by the public and the science community. And so that's a big part of what the missions ultimately need to do. And what is going to be contained in those data products and how they will inform the science goals and objectives needs to be part of the traceability matrix. And ultimately that arrives over here on the right as specific requirements that are laid out for the mission and how its success will be defined. So that's kind of the story about traceability. And it sort of drives the entire process of developing these missions and sort of retrospectively looking at how they perform. So as I said on the previous slide, I want to highlight or emphasize the sort of data product piece of that pipeline, because that's where a lot of the work that we've done on uncertainty quantification comes into play, and where I think some of the themes of the workshop really hit home with what we're trying to do with these data products. So here's a sort of an overview of the data product pipeline for a lot of these earth science missions. There's sort of nuances for individual applications or individual missions on what these actually look like, but this is sort of a broad categorization that a lot of the missions adhere to. So on the bottom is an example of what's called a level 1 data product. This is basically the radiant spectra that are observed by the satellites in space. So that's what constitutes level 1. This is an example for OCO2, basically just summarizing the intensity of radiation that the satellite observes over the range of wavelengths that is designed for a particular location and time on the surface. And then there's subsequent levels of data products that add additional utility, particularly for the science community, but also involve additional steps of processing. So the next level is level 2, which is some estimate of a geophysical quantity of interest. We'll talk about, for example, atmospheric carbon dioxide. And that is, there's a process that involves going from that level 1 to that level 2 data product that we'll talk about shortly. And then there's subsequent levels of data processing and data products that are available for use by the scientific community. So we're going to talk in the rest of the presentation here about the carbon cycle in particular. And what this translates to for the case of the carbon cycle is outlined on the slide here. And I want to sort of motivate this with the figure at the bottom, which sort of gives a very high-level view of the carbon cycle, the global carbon cycle, and what some of the key questions and sources of uncertainty are in monitoring the carbon cycle. So the figure kind of shows that you can sort of visualize the carbon cycle as this kind of small collection of reservoirs of carbon storage. And so here we've got the atmosphere, land, and ocean. And then this figure particularly parses off the available reservoir of fossil fuels. And then all the arrows in here basically give estimates of the exchanges or the fluxes of between these different reservoirs. And so there's, even in the absence of the use of fossil fuels, there's these exchanges among the land, atmosphere, and ocean at particular rates in the natural carbon cycle. So the magnitudes of those exchanges are fairly large, as you can see, relative to the fossil fuel piece. But if you actually look at sort of the net exchanges, the differences between the land and atmosphere and the ocean and atmosphere, then you start to get an order of magnitude of the fossil fuel, which is essentially a perturbation. And that's really the uncertainty tied into the magnitudes of all these fluxes is really what's tied into a lot of the science questions driving carbon cycle science is understanding this balance about these carbon flux exchanges. So in the remote sensing realm, there's a progression of these data products that translates to trying to estimate these quantities of interest. And so these fluxes that are at the bottom are actually at the end of this pipeline. There are level 4 products that are eventually produced that estimate these fluxes, but there's a progression of these lower level data products that sort of lead up to that. And so this notion of traceability enters into all of this because there are various sources of uncertainty across this progression of data products. The one I'll talk about in particular is going from level 1 to level 2. So I'll show an example of that in a moment. I want to set the stage with a little bit on the background of these carbon cycle monitoring missions. So the story is that using satellites to estimate carbon dioxide in the atmosphere can really provide a lot of valuable information about what's going on with the carbon cycle globally and regionally and across time. And so NASA's had now a couple of missions that are monitoring the carbon cycle, OCO2 and OCO3, orbiting Carbon Observatory 2 and 3. And going back to what we talked about at the beginning of the talk, the science motivation for the missions was on getting precise estimates of these fluxes between those different reservoirs in the carbon cycle. At the same time, the actual science traceability matrix that emerged for OCO2 and OCO3, sort of on the right side of that traceability where we're talking about what the instruments are, what they're measuring, and what the requirements are, those are actually set up to focus on the concentration of carbon dioxide in the atmosphere. And in particular, a quantity of interest that these satellites are targeting is called XCO2, which is basically the column integrated CO2 concentration from the surface to the top of the atmosphere over a small spatial footprint like those on the right side of the slide here. So the quantity of interest for these satellites is called XCO2, it's atmospheric CO2 concentration. So as the missions have evolved, the science story has evolved a little bit as well. OCO2 has been monitoring now for since 2014, OCO3 since 2019. So that's an extended period of time. And it's sort of opening the opportunity to look at sort of the long-term evolution of the carbon cycle over the course of those missions. Okay, so here's sort of a pictorial view of what this data product pipeline looks like for these missions. On the upper left is, as we had seen previously, an example of level 1 data product, which is the observed radiation by the satellite across a range of wavelengths. And then that is processed into level 2 products. So this is like a small segment of an orbit of OCO2 over Western North America. And you get these fine spatial scale estimates of that quantity XCO2 shown here in the upper right. Then these can kind of be combined together to give sort of more gridded regular spatial and temporal coverage estimates of that CO2, and then we can sort of see the fairly complete spatial coverage over the course of, say, a month of observation here on the bottom left. Although the coverage is not totally complete because of unavailability of data due to things like clouds and low sunlight areas as well. And then finally, on the bottom right, is these lower level products can be used to estimate these fluxes, the exchanges between the atmosphere and the land and ocean. And that's an example of that on the bottom right. Now, the other thing you'll notice in this slide is actually Bayes' rule written down a couple times, because not only is this a flow of data products and processing algorithms, but it's actually a flow of inferences. The movement from one level to another in a lot of instances with these data products involves some sort of inference. And we need to sort of trace the uncertainty quantification through that pipeline. So I'll spend a little time here talking in more detail about some of the important implications for that level 2 part of the problem, basically going from the satellite spectra to the estimates of the geophysical quantity of interest. And so that's the level 2 problem. And there's a very broad history and literature on this topic. It's called a retrieval. And it's fundamentally an ill-posed inverse problem. And the overall objective is to infer an unknown surface and or atmospheric state from the remote sensing observations of radiation. So our remote sensing observations at level 1, we're calling those Y, or the radiances. And X is our state of the atmosphere. In the case of OCO2 and OCO3, that's the CO2 concentration, along with some other properties of the atmosphere and the surface that we may not know. For OCO2 and 3, aerosols in the atmosphere are very important. The reflectivity of the surface of the Earth and the ocean is also very important. So the schematic here at the bottom just shows sort of on the left, sort of our view of sort of how this works in reality. Like there's some sort of fundamental forward function that would map the states to the radiances. We don't know everything about how that physical process works, but we try to capture that through a fairly realistic physical forward model. And then that all gets sort of pulled into the retrieval algorithm, which is over here on the right, to produce an estimate of the state, which we call X hat. And so the other thing on here is that some of the key sources of uncertainty are sort of laid out in words on the slide here. And there are a number of sources of fundamental epistemic uncertainty in this problem, including how that forward model is structured and some of the other inputs that go into that retrieval problem. So how this is done, I'm just going to say this very briefly on this slide, and the details are here. Operationally, we work with what we might call a working model with a working forward model F, which is sort of our best representation that we can do computationally, and given the knowledge we have about the problem, that's our working physical forward model. And then we also have to have working estimates of a lot of parameters that go into that model. That's this E here. And then how this is done operationally to basically use this information in a Bayesian context with some assumptions about the prior state of the atmosphere. And then we sort of solve that inverse problem to get an estimate of the state. And that XCO2, our quantity of interest, is basically a weighted average of the retrieved atmospheric CO2 that comes out of the retrieval. So because there are these sources of epistemic uncertainty, the estimate is not perfect. The other thing that happens operationally with these products from OCO2 and OCO3 is they actually go through a bias correction procedure, and using available ground validation information. And this, again, with the theme of traceability, provides some traceability to observing standards. And so it's sort of, in a pragmatic sense, a useful thing to do, but it also has has some drawbacks in terms of having incomplete uncertainty quantification. So here's just a couple of maps of what this looks like. These are all from OCO2, and they pick up a lot of the key features of the carbon cycle globally and seasonally, with the XCO2 products that come out operationally. The next couple of slides, I just want to mention a couple of other things. That state vector includes other unknown quantities that you might call nuisance variables, or interferences, as they're called in the remote sensing community. These are some examples. So the surface albedo and aerosol concentrations are big ones in this particular problem. Another one that is part of the problem is something that's called solar-induced fluorescence. And the sensitivity of the radiation observed by these satellites is actually sensitive to this quantity. And it's essentially radiation that's emitted by plants as they're undergoing photosynthesis. And the range of wavelengths seen by these instruments is sensitive to this quantity. Well, as the missions have evolved, the science community has actually realized that this actually has a lot of scientific value, because it's giving an estimate of the activity of plants. And so it's actually become a very valuable product to these missions, when it was originally thought to be sort of a nuisance parameter that the satellites had to worry about. So this is an example of the science traceability and the science story sort of evolving as the mission goes along. Okay, so in the time I have left here, I just want to say a couple things about approaches that we're using to be more comprehensive in the uncertainty quantification for this pipeline, particularly for these two missions. So one thing that we spent a lot of time is simulation-based uncertainty quantification, where we're essentially simulating that level 1 to level 2 pipeline by simulating a large ensemble of synthetic gradiences and putting them through that retrieval pipeline. An important part of that, a couple important parts of that process, is we also introduce a fairly well-calibrated model discrepancy, so that we have the realistic situation of an imperfect forward model that goes into this retrieval pipeline. And then we can use that ensemble of synthetic true and synthetic retrieve states to get a probabilistic characterization of the distribution of the errors and other conditional distributions that we might be interested in. So this model discrepancy actually enters into in the space of the spectral observations. So this slide just shows sort of an example of what these look like across the three bands of the spectrum that OCO2 observes, and under a range of geophysical conditions. Oops, sorry about that. Okay. And then one other thing I just wanted to highlight about some recent work that we've been doing in trying to tie all of this together with the different information that we have about uncertainty for these missions across the simulation approaches and as well as validation data, is we very often see these epistemic uncertainties manifest themselves as errors in space and time that have coherent structures, kind of like what we see in these two examples from OCO3. These are very characteristic patterns of what we'll see over a small patch of an orbit. Errors that are fairly strongly correlated spatially, and there's very fundamental reasons that explain how that can happen. And it's an important thing that needs to be propagated to the processing chain down the line. And so we're spending some work trying to quantify this essentially through sort of a random effects type of approach that captures the variability in this epistemic uncertainty in these products. And the maps here just show some estimates of that under different observing conditions for OCO2 on the top and OCO3 on the bottom here. Across the two missions, there are some subtle differences in the behavior of these, but by and large, there are a lot of commonalities across the two missions as well, where the biggest challenges are at very high latitudes or high elevations over land, and things are a little more uniform over the oceans. Okay, I just want to say a couple of things about some higher level products and then wrap up with some concluding thoughts. So level 3 is sort of the next piece of the pipeline, and this particularly becomes important when we want to potentially get a best estimate of, say, XCO2 from a combination of these satellites like OCO2 and OCO3. There'll be other missions coming online that will be making similar observations. And this is where things like spatiotemporal data fusion become pretty important. And the propagation of those sources of uncertainty from the lower levels are very important here as well. But a lot of the methods here can make use of that information and combine them in a probabilistic coherent way. And then finally, the last step of the pipeline is that level 4, where we're actually estimating those fluxes, those carbon fluxes across the different reservoirs. And this involves another inference or another turn of the inference crank, if you will, because these inversion systems, as they're called, use as their data, essentially the estimates of the atmospheric CO2, and they combine with a physical model of the transport within the atmosphere to try and estimate those sources and sinks. So the sources of uncertainty that I talked about already enter into that problem, as well as other sources of uncertainty in that atmospheric transport model as well. And there's now particularly for OCO2 and OCO3, there's a particularly sizable collection of these inversion systems. And so there's probably some work to go, but there is methodology out there for making the best use of all of the combined information to incorporate those additional sources of uncertainty. Okay, so I think I'll wrap up here with a few thoughts. I mentioned earlier this notion of traceability, and now, like in the case of this carbon cycle science mission record, that these missions are now in an extended phase where this data record is growing. And as I mentioned before, the traceability story sort of evolves as well, and that's something that gets revisited as the science community makes more and more use of the data record. But as more satellite instruments enter the constellation, that presents another additional challenge for the continuity of the data record going forward. And I also think it's a very interesting time for the carbon cycle in particular. In the years to come, there's going to be a lot of opportunity to try and understand how the carbon cycle is interacting with the other Earth system processes. An example, I think maybe people have been hearing that there's a potential super El Nino on the horizon. And I think this carbon cycle community is going to be very interested in the impacts of that on the carbon cycle and how that interacts with the other Earth system processes. So there's work to go, and we're on the UQ front. We're sort of heading in a direction for this work and other work to look at for the level 2 problem, joint uncertainty quantification for those aggregate estimates that we need in these applications. So I'll stop there. Thank you.